In homework 5 in unit 3, we're going to be looking at logarithmic functions. Now, logarithmic functions and exponential functions are directly related. So homework 4 and homework 5, those functions are inverses of each other. So let's go ahead and talk about logarithmic functions. Logarithmic functions have a specific format, and they also have a specific graph that transformations can take place on, just like with exponential and other basic graphs. So one way that we could see a logarithmic function written is y equal log, and then this subscript is a base, so it's not log b straight across, it's log base b is how we say this, of x. Now a lot of times you don't see parentheses around the argument of a log, so sometimes you'll see these parentheses and sometimes you won't. You can also see this written as log base b of x equals y. So the y can be on either side. So this is called logarithmic form. So log form we'll call this. And the base of this particular log is b, so log base b. Well, we know the word base from something else. We know the word base from exponents. So if we used b for our base, our exponent would be y equals x. So this is exponential form. So if the y is on the left, and it doesn't really matter, what ends up happening is you always start with the base, you go to across the equal sign, and then you go over here to the right hand side to the argument. Now in this one, this would be log base b of x equal y, so b is base to the y equals x. So these are the same thing. This is called exponential form. And it's going to be really important that you be able to work with these back and forth from log form to exponential form in order to clarify what's going on here. Now let's go ahead and look at the log graph. Now there's a lot of different types of logs because we just need to change this number for the base and we have a different graph. But the general idea, the general sketch is the same. So we're going to look at two different graphs here. We're going to look at log base 10 of x. This is called the common log. It's called the common log because of the base 10. And a lot of times you will not see this base 10. What you'll see is just y equal log of x. So if you don't see a log and it's written in this format, they mean base 10. It's called the common log. Now if you look on your calculators, you'll see a log key as well, and I'll show you how to work back and forth between the log, the common log, and other logs. Another graph that you're going to see, or another way that you're going to see this, is written with natural logs. So if we have log base e of x, this is called the natural log. And we call it the natural log because the base is the natural number. Now you usually see this one not written as log base e of x, but you usually see it written as ln, so ln for natural log of x. And again, you won't always see parentheses after the argument of the log, but I usually try and put them in just to clarify what's going on here. So to get started, we already know a lot of things about functions and their inverses. We know that they're symmetric across the line y equal x. Now if you remember from an exponential function, it always goes through this point. If I plug in a 0, I get a 1 back. Okay, so we could look at something, let's say like y equal 10 to the x from our last section, and we would get this graph. So this is our exponential form. Now over here, this point 0, 1 would reflect to the point 1, 0, because remember the domain and the range swap between a function and its inverse. And then what ends up happening is it reflects across the y equal x line. Whoops. Sketch that in a little better. And so you can see that they are reflections across this line. So this is your exponential graph up here, and this is your log graph down here. Now remember, they're inverses of each other. So logs and exponentials are inverses. Now the bases have to be the same, but you kind of get the general idea. If we can match up those common bases, they're inverses of each other. So this is the basic log graph. So if we were to talk about the log graph without a transformation, let's go ahead and talk about its domain and range. Well, domain, it looks like this gets very, very close to x equals 0, but it never quite touches it. So I'll start this with a 0 with a parenthesis because I don't have equality at 0. And I'll go off toward infinity. All my x values go off toward infinity. And then I also have my range. Now you can see range is vertical, and the ranges look like they start here at negative infinity and go off toward positive infinity. And of course we never bracket infinity. So those are the domain and range of a standard log graph. Now if we do any transformations on the graph, of course this can change. Now the log graph, just like the exponential graph has a horizontal asymptote, the log graph has a vertical asymptote right here, and this is the line x equals 0, because I'm never going to cross this line. Okay, and it's just basically telling us that you can't take the log of a negative number. So that's an important thing to remember as well, because the domain is 0 to infinity. What that translates into is you cannot take the log of a negative number. And that's good to know. It might save you some trouble when you're trying to do that for a problem and you realize it's not possible. And so you can just go ahead and start working on something different with that problem. Say it's no solution. So you cannot take the log of a negative number. Now there's a lot of other characteristics of logs that we're going to be talking about now. There's a lot of properties of logs that we don't cover, and while we're working through problems, if any show up, I'll kind of add to the list. So the first one I want to look at is log base b of b. So basically, if I replace these with numbers, they're saying the base and the argument are the same. What does log base b of b equal? Okay, well, this means b to what power, so b to what power equals b. Because remember, we start with the base exponential form, so b to what power equals b. Well, we know that what this is 1. B to the first equals b. So log base b of b equals 1. Now this is true for any values I can plug in here. 2, 2, 5, 5, 100, 100. It doesn't matter as long as the values are the same. Now you can't have negative bases, and you can't have negative arguments because you can't take the log of a negative number. So that's an example of log base b of b. Let's look at another one. Let's look at log base b of 1 equals what? So if we rewrote this in exponential form, we'd start with b to what power equals 1. So b to what power equals 1? Well, anything to the 0 power equals 1. So log base b of 1 equals 0. Another one that we'll run into, let's see if we can squeeze it on here, log base b of b to the x equals what? Okay, so that's what we're trying to figure out here. So again, b is my base, so b to what power, so b to what power equals b to the x. Well, we can see that the bases are the same, so the exponents have to be the same. So basically, it has to be x. So b to the x equals b to the x. Okay, so what that's saying here then is this entire expression on the left is equal to the expression on the right. So this is also giving me another quick little shortcutter rule that I can follow. Log base b of b to the x, I can take this exponent and pop it out front, and I'd have x times log base b of b. But we already know from up above that log base b of b is equal to 1, so this is just equal to x. So the rewrite here is I can take the exponent of the argument and pop it out front to simplify working with logs a little bit. So these are just some of the rules that we might come across. I think one other important one that we can note down is an exponential form. If we have a base of b and we have the exponent is log base b of x, these b's basically just cancel each other out. So this log of b and this base of b cancel each other out, and you're just left with basically the argument of whatever this log is. Now in order for this to work, the argument for my base and the argument for the base and my exponent have to be the same. So these are just some examples of some shortcut rules, if you can remember, that will be really helpful for you. Now this is going to be a big one. This is called log conversions. So this is called a log conversion. Now some of you will need this and some of you won't, depending on the calculator that you have. So let me go ahead and pop in a calculator real quick. Now the calculator that I will be using, if I look under the math menu and I can do it in graphing or outside graphing, it doesn't matter, math, and then I can either scroll up or down. If you notice, I have this nice little key that says log base. And if I select log base, it gives me an opportunity to insert my base in my argument, and then I try and use this to solve and to graph. So this calculator that I'm using has a log base key, but a lot of your calculators don't. So the question is how do we work with a calculator that doesn't have that to solve the same types of problems? And that has to do with our log conversion. So for a log conversion, we might have a problem, let's say, like log base b of a. This converts to log of a over log of b. So I can work the same problem with a different base, and I can convert it to a common base. Because remember, when I have just log of a, that means common log. Now on your calculator, you have a log key right over here on the left. So if I can exit out of there. So if I hit this log key, remember that's implying that the base is of a base 10 here. So this is your log key. Now if we need to use the natural log, this is log base e, and then I can put in my argument. So this is called a log conversion. Now I can convert my logs either using natural logs or common logs. Again, this is called the common log. So this would also be the natural log of a over the natural log of b. So this is my log conversion. This is going to be really important to be able to work with for graphing and for solving. Now, a couple quick things. Don't forget, log of a means base 10. Natural log means base e. If you have any other base, you have to be able to write it in this form. You can't drop the base here. Now, one way I remember this conversion is this looks kind of like a fraction. The a looks above the b, and so we can think of this as the numerator and the denominator, the a and the b. So the argument over the base. Bases goes in the bottom. So those are a couple of quick ways to work with a log conversion. Well, let's put some real numbers to this and see what we can come up with. So let's look at log base 9 of 81. Well, we can imagine what the answer to this is. 9 to what power is 81? And that would be 2. 9 squared is 81. So we know the answer is 2. Let's go ahead and look at our log conversions. Our log conversions for log base 9 of 81 would look like log of 81 over log of 9, or, and it doesn't matter which one I use, natural log of 81 over the natural log of 9. So let's go ahead and pop back into our calculator and see what we get here for those answers. Since we have the natural log of up, let's go ahead and use that. So natural log of 81 divided by natural log of 9. Now remember, when I'm using the natural log for the numerator, I also have to use it for the denominator. And you can see we get 2 here for our answer. So this is my log conversion. Log of 9 divided by log, and I have to stick with log of 9. Whoops. I have to do log of 81 in the numerator. So I have my log of 81 over log of 9, and you can see that I get my answer of 2, which is what I expected to get anyway. So let's go ahead and pop these into the lecture so we remember what our log conversions are. And these are going to come in handy a lot, so please make sure you have note of them in your notes so you can go back and grab them anytime that they would be handy for solving problems or for graphing, because we're going to use this in graphing. Now if your calculator has a log base key, log base 9 of 81, you could just go ahead and use that. So in my calculator it's math, and you can scroll up or down to get to log base. So log base 9 of 81 should be 2. And so that's another one that I have here. If you have the log base key on your calculator, it's really handy for checking answers and for graphing. Okay, so working with these by hand, the log conversion will be handy. I should be able to talk about this anyway in exponential form, because in exponential form 9 is my base. So I'd start off with 9 to the second equals 81. So this is 9 squared equals 81, so I know my solution is 2. So that's a log conversion. We're going to be using it quite a bit. Now transformations on the graph work the same as they have for any other transformations, but let's go ahead and run through a few quick examples. Now I won't graph these out, but we'll kind of just list what the transformations are. For instance, let's go ahead and start with one. G of x equals 9 plus log base 2 of x. Okay, so if you notice here, there's nothing really going on. I have my base and my argument. What's happening here is with this 9, because it's outside the argument, this is a vertical shift, and it will go up 9 units. Now if this was a negative 9, it would go down 9 units. So that's one type of transformation that you'll see. You'll also see sometimes when the argument is changed. So here you might have something, let's say like log base 5, and this is where it's important to have the parentheses of x plus 9, because if you don't have parentheses, the only thing that is the argument of my log is what's directly after it. And we'll do a minus 7. So here we have two transformations. We have the x plus 9 and we have the minus 7. Well, first of all, for my negative 7, this would be a vertical shift down 7. Okay, now from over here with this x plus 9, because it's within the argument, it's opposite of what you'd think. This is a horizontal shift. Now it's a plus 9, so I do opposite. Horizontal shift to the left 9 units. So again, it matters whether it appears in the numerator or the denominator, or sorry, it matters whether it appears in the argument or outside the argument. In the argument, remember, it's always opposite of what you would think. Now the other type of transformation that we often talked about was reflecting across an axis. So let's go ahead and look at another example. G of x equals, let's say, minus ln of x. Well, what our transformation here is just this negative sign. So this negative 1 that's out front, because we could put a 1 here. This is a reflection across the x-axis. Now if the negative was on the inside of the argument, it would be a reflection across the y-axis, but I don't think you run into any of those in your homework set. So to continue, let's go ahead and pull a problem in from my math lab, and we'll actually work through the problem, and then we'll look at our solutions. So here we're graphing g of x equals 3 minus ln of x. So we can see right away we have a vertical shift up 3 units, and we also have a reflection here in front. Well, let's go ahead and take care of that reflection first. The first thing that we're going to look at is which one is the graph for an ln. It's this upside down piece right here. This has negative concavity. This one over here is an exponential tool. This is your logarithmic tool. So as soon as you click on the graph, it gives you these options to adjust the graph. Well, in this particular case, we have a vertical shift up 3 units, and then the negative sign means I'll reflect over the x-axis. Okay, now next, if you read through the directions, it says use the graphing tool to graph the function, graph the asymptote as well as a dashed line. So let's go ahead and grab the line now. The asymptote is going to run from here right along this y-axis, and we want to make it dashed. So let's go ahead and check our answer there. Whoops, I got something wrong, so let's go ahead and have a look. Okay, so if I click on my graph again, okay, so let's go ahead and see what we have going on. I better clear, first of all, what I had. Grab that again. So vertical stretch shrinking, horizontal stretch shrinking, that's not right. So I have my 3 as my vertical shift, so I need to make sure I have that in. There's no horizontal shift, it's reflecting over the x-axis. So, oh, I see what happened. So when I did that, my vertical shift went to a negative sign here. We need to make sure it stays positive. So I think we have everything here. Now we want that to be a solid graph, and now we want to graph our vertical asymptote as a dashed line. Let's check it now. So be careful when you're doing this same problem, because what happened when I hit that reflection, it made my vertical shift and it negated it. So here's my correct graph. What is the equation for the vertical asymptote? Well, this vertical asymptote is the y-axis, which is the equation x equals 0. Next, it's probably going to ask me for my domain. Now remember, for our domain, I cannot take the log of a negative number, so this has to start at 0 and go off toward positive infinity. And I can see that from my graph. You can see the vertical asymptote says I should use a parenthesis, and my x values are going off toward positive infinity. Okay, the next is looking for my range. Now this one's a little bit tricky. For my range, it kind of looks like it's getting closer and closer to the x-axis but never crossing, but I can cross the x-axis because I can come up with some pretty large numbers for this piece, and 3 minus a large number would put me in the negative vicinity. So what I have here is from negative infinity to positive infinity. So it looks like there's an asymptote there, but really there isn't, so you have to be careful about that. So that's how you'll run through one of these problems that you'll get in your homework section. I think this was number 34. Let's go ahead and pop these into our notes so you have some references there as well. So when we're working in graphing, we need to kind of be aware of the original domain and range. That'll help us find the domain and the range of a transform graph as well. Now, one thing that we didn't talk about is how we would graph this on our calculator to kind of check our work. So let's go ahead and graph 3 minus ln of x on your calculators. Now if we graph 3 minus ln of x, you don't need to have a log conversion here, so I can graph this directly, but we'll also look at an example where I can't and I have to do a log conversion. So let's go ahead and pull in our calculator, and let's hit y equal, and again it was 3 minus ln of x. Let's hit graph, and now you might have to change your window depending on what we were graphing with before. I think I'll change my y values here. Let's change everything, negative 10 to 10. And I think that there's a zoom standard or something like that under the zoom key, if you'd rather use that. I like always changing these by hand because it kind of reminds me what I'm working with. It still kind of chops this off a little bit. So we know that it continues to go up, so we have to have some knowledge about the graph, and without that knowledge of the graph, you know, the graph doesn't look correct, so I have to be really careful about that, but I know it continues to move up. So that's how we would graph on our calculators. Now sometimes that's not going to work out because I'm going to have another base other than just the common log or the natural log. So quick edit here, this line continues up toward positive infinity, and I have a vertical asymptote here as well. Let's go ahead and graph another different base, not just the base that's a base e or the common log, but let's look at a graph of a base that's a little bit different, and when we look at that different base graph, I have to do a log conversion in order to graph. So for this next problem, let's go ahead and look at g of x equals log base 5 of x plus 5. So notice over here my log was log base e, and I have a key for that on my calculator. This is log base 5 of x plus 5. Well, this is just a standard log graph converted to the left 5 units. Okay, we should be able to recognize this. So if you have the log base 5 key on your calculator like I showed you before, this is easy. So let's go ahead and look at that, log base 5 of x plus 5. So under y equal, we go with the log base key. So I go to math, and some of you won't have this key, this log base key. So this is log base 5, and then the entire argument has to appear in the parentheses of x plus 5 in the graph. So it's just what we thought, it's the log function that's moved to the left 5 units. Now it's not showing this, but this goes down forever, and I have a vertical asymptote here. So let's go ahead and pop this in. Now remember, if you don't have that log base key, we can still graph this using that log conversion that I showed you. So let's go ahead and fill in the rest of this graph, because again, your calculators don't quite get it all right. It gets confused by the asymptote. Now the asymptote used to be over here at x equals 0, 1, 2, 3, 4, 5, but now I need to move it 5 units to the left. So this is my new vertical asymptote, and this is the line x equal 5. And so the rest of this graph basically comes down and gets closer and closer to that asymptote but never crosses. So that's what that graph looks like. Now, how would I graph using a log conversion? I would graph this, remember it's always the argument over the bottom, so it would be log of x plus 5 over log of 5. Or, remember, you can also use natural log of x plus 5 over natural log of 5. Either one of these will produce the same graph. So let's go ahead and pop back into your calculators. If you don't have the log key, this is how you would graph. So you would just graph log of x plus 5, make sure you close parentheses and divide, over log of 5. Okay, and that's identical to the graph that we just had. And remember, we had to do some fixes on that graph. We had to put in our vertical asymptote and extend this as well. So that's the log conversion that you would use. So I could also use, I'm going to put this on my second line, ln of x plus 5. And when we graph these, you're going to see that they're identical graphs. They run right over the top of each other, over ln of 5. Let's go and graph here. So here's the first one. You might be able to see this little red line coming up on top. That's basically saying it's the exact same graph. So for a log conversion, what I would do is I would plot these values. See if I can get those to show up to throw into my graph or to my lecture. So these are the log conversions that I could use. Now both of those will produce the identical graph to the graph that we have. And again, it's just a quick way to check the log conversion to see what's going on there. So either one of these will produce the same graph. Okay, what we're going to do for the rest of this lecture is we're just going to run through a lot of different problem types that you'll see during your homework set and on quizzes and exams. So for instance, you might have the equation 4 equals log base 7 of 2401. And they want you to put this in exponential form. So exponential form, what we can do then is start with the base. So exponential form would be 7 to the 4th equals 2401. Okay, so this is the log form, this is the exponential form. And you really have to do a lot of these problems to get used to working back and forth. And this homework set is long, I think it's 40-some questions, but a lot of the problems are just short little problems like these converting to exponential form. So they're not that bad. So exponential form here, again we start with the base, and it doesn't matter if the 5 is on the right or the left, you always go to past the equal sign. So this would be 3 to the 5th equals m. Now be careful in your My Math Lab, if this is a capital M, you have to make sure you input it as a capital M and not as a lowercase m. So let's go ahead and look at an example where we have something going on the right. So we could have log base 4 of 16 equals y. So when I convert this to exponential form, I still start with that same base, base 4. I always go to after the equal sign, so 4 to the 6th. I'm sorry, this should be a y. 4 to the 6th is not 16. This is just a y. This is just our argument y. So this is 4 to the y equals 16. So this is exponential form. Now we're not being asked to solve, we're just being asked to rewrite this in exponential form. Now sometimes we'll be given exponential form and asked to convert it to log form. So this would be something like 8 to the 3rd equals 512. So log form we start with the base. This is my base. So when we start writing, we have log. Our base is 8. Now remember, it always goes to after the equal sign. 8 to the 3rd equals 512. So 8 to the 3rd equals 512. So that is converting from exponential to log form. Now not all of them will be as straightforward as this one. We could have something like 1 over 125 equals 5 to the negative 3. And we could ask to put this in log form. Okay, so our base is 5. So I'm going to have log base 5. Now it's 5 to what power? Negative 3 equals 1 over 125. And so this is my equivalent log form. And again, working back and forth between these is going to be really important. Now sometimes you'll have to get rid of a radical before you can get it put into a log form. For instance, the square root of 25 is 5. That would be the same as 25 to the 1/2 equals 5. And then in log form, this would be log base 25, because this is our base, of 5 equals 1/2. So the way that we write this, 25 to the 1/2 equals 5. So sometimes you'll need to rewrite these a little bit in order to get them into the appropriate form. So converting back and forth isn't too bad if you remember the rules. They're usually not too bad. A lot of times when we're simplifying expressions, we can use our calculators to help us check some answers. So let's go ahead and look at some examples where we can do that. All of these have been rewrites. Now we're going to be asked to solve. Now some of the directions say without using a calculator, but my math lab doesn't know whether you're using a calculator to check your answers or not. So I encourage you to always check your answers before you submit them, especially on a quiz or a test. So let's look at some examples. Let's look at log base 14 of 1/14. Okay, well in exponential form, what this would look like then is 14 to what power is 1 over 14? Okay, well 1 over 14 is 14 to the negative 1. Now that I have these equivalent bases, that means that my power that I need here is equal to a negative 1. So log base 14 of 1/14 is equal to a negative 1. That's my answer. So log base 14 of 1/14 is equal to a negative 1. Now let's go ahead and pop this into our calculator to check our work. I have a log base key, so I'm going to use my log base key, and then we'll also show how to use it without the log base key. So here I have log base 14 of 1/14, 1 divided by 14, and you can see I get negative 1. Now what about log conversion? Okay, well remember you can use log or natural log. It would be the log of 1/14, because remember this is base so it goes on the bottom, divided by log of 14. We'll get negative 1 out of that, and I can do the same with natural log. You don't have to do this all these different ways. Just choose your natural log or your common log to use. But I'm just trying to show you here that it doesn't matter. You get negative 1 no matter what conversion you use. So always take the time to check these. And like I said, especially on a quiz or a test. Because when you have these on a quiz, if you get them wrong, you have to redo the whole quiz. And same as on a test, you don't get a second chance at those. So these are some examples of how you can check that with your calculator. Okay, let's run through a few more of these. Let's look at log base 3 of the square root of 3. Okay, so this is log base 3 of 3 to the 1/2. The square root is the same as the exponent of 1/2. So remember, using my rules of exponents, I could pull this 1/2 out front. So I'd have 1/2 log base 3 of 3. And we know log base 3 of 3 is equal to 1 from my list at the very beginning of those values, because 3 to the first power is 3. So I'm left with 1/2 times 1, or 1/2. So my solution here is 1/2. So log base 3 of the square root of 3 is equal to 1/2. Okay, so let's go ahead and look at this one as well on our calculators to check our work. So let's look at that log base key. So log base 3, and my argument goes the square root of 3. I should get 1/2, 0.5. Equivalent fraction. If you want to convert that to a fraction, you go to math frac, and it converts to 1/2, or you could do your log. So I'd have the log of the square root of 3, and I can use natural log here as well, don't forget. Now that parenthesis is kind of in the wrong spot. I need to arrow out first and then close my parenthesis. So log of 3 divided by the log of square root of 3 divided by the log of 3. And remember, base goes in the bottom. Get 0.5, and again I can convert that as well. So some of these kind of fell off the screen a little bit. So let's go back up where we can see there. We'll pull these in and put these in the lecture so you can see the appropriate keystrokes for checking your answers. So it's worthwhile to do that log conversion to actually check your work here. Now when you're taking your quiz for this section, knowing that log conversion is going to be really important. That's definitely going to come up. So make sure you have that in your notes. It'll also help you out during the homework problems. So these are a lot of examples that we've looked at so far with converting and rewriting. Let's look at log of 1 over 100. Now wait a minute, this is strange. We don't have a base here, but remember, this is the same as log base 10 of 1 over 100. It's called the common log, but if I use my log key on my calculator, I don't need to worry about this, but we'll check it with that. So this means 10 to what power is equal to 1 over 100. So we'll call this, let's say, y over here. So 10 to the y equals 1 over 100. Okay, so continuing on here, this is 1 over 10 squared, and then if we flip that up top using my negative exponent, I can see that y equals negative 2 then. So my answer here should be negative 2. So let's go ahead and check this out on our calculator, log of 1 over 100. Now I can just use my standard log key. I don't have to do any conversions. I just use my log key because I'm using the common log. Let's get to a blank screen here. Okay, so log of 1 over 100. So no conversions here because I'm using a common log, and you can see I get negative 2. So do your handwork, and then after you get your handwork done, go and check this on your calculator, because we don't want to submit incorrect answers. We could kind of catch that before we submit it if we just give it a double check on your calculator. Okay, so that's another way of finding or verifying your solution. Now you're going to run into these with some natural logs as well. So we might have something like the natural log of 1 over e. Okay, well this looks strange because we don't have a base here, but remember this is log base e of 1 over e, we'll say equals y. So when I rewrite this in exponential form, I say e to the y equals 1 over e. Okay, e to the y, well this is the same as e to the negative 1, y equals negative 1. So that should be my solution here, but let's go ahead and double check it with our calculator, natural log. So I'm going to use my natural log key, 1 divided by e. Now when you use e, sometimes it's going to want an exponent on the e, and if it's just good old e, put a 1 for the exponent. If it doesn't ask, then you're good to go. So that does verify that we are correct. I get a negative 1 there. So running through these problems, it is a large homework set, but a lot of the problems are just these really short problems where we're converting logs and working from there. We do have a couple of story problems, and these aren't too difficult, but I want to bring them up real quick just to show you how to get started with them. So the example that I'll look at first, this would be similar to problem 40, I believe. To pull up. There. So again, this is similar to problem 40. Go ahead and take a minute to read. If you want to pause, you can. This says the percentage of adult height attained by girls who are X years old. So we know right away we have a variable. X stands for their years old, can be modeled by this function. So again, X is years old, where X represents the girl's age from 5 to 15. Now this is interesting. We can't plug a 4 in here because 4 minus 4 is 0, and I can't take the log of 0. Remember that vertical asymptote we had. Use this function to determine approximately what percent of her adult height girls are at age 6. So we're trying to predict their adult height given their height at age 6. So in place of X, we would go ahead and put in a 6. So it's this equation, I just go ahead and plug in a 6. Whoops, I forgot the log in here though, better get that in. So 35 log and again we plug in a 6. So let's go ahead and plug this into your calculator. We have to be really careful about order of operations. I don't do this addition first. I do the log first and the multiplication. So 62 plus 35. Now this is just a common log, so I can use my log key. And then in my argument, I would have my 6 minus 4. And if you want to just put in a 2, that's fine. And so this is my answer. And then it has specific directions about rounding. So let's go ahead and pull the whole thing in, and then let's make sure that we round it correctly. Okay, so it says round to 2 decimal places. Well, this would be 72.5. Now my second decimal place right now is a 3, but the 6 rounds this up to a 4. So 72.54% of her adult height. So this answer right here would be that 72.54%. So you have to make sure that we round these correctly. They are a little bit picky about the rounding, so don't make any intermediate rounding with your calculations. For instance, don't take the log of 2 and then write it down as just 1 decimal place and then finish the problem from there. Okay, the last problem that we're going to be looking at deals with decibels. Okay, so go ahead and take a minute, pause, read through the problem, and see what we have. So this is the equation that we're using right here. Let's see what everything is. I represents intensity. Decibel ranges from 0, which is barely audible, to 160, which can rupture your eardrum. This says the sound of a certain animal can be heard 500 miles away. So I wonder if this 500 is a useful number or not. Reaching an intensity of 6.2 times 10 to the 7th. Well, that is our value for I here. That's the intensity. So let's go ahead and plug that in. 10 log. Now this one's going to be a little bit tricky. It's 10 to the 12th. And then my intensity will be 6.2. So this is times 6.2 times 10 to the 7th. And again, that number is coming from right here. So let's go ahead and figure out D, which stands for decibels. Let's plug this into your calculator. So this would be 10, and we're just using a log. And our formula here was 10 to the 12th, so 10 exponent 12. Make sure you use parentheses if you need to there. And then for this one, for the intensity, we're putting in 6.2. I'll put in a time sign just to be careful. 6.2 times 10 to the 7th. You don't need 2 times sign, so 6.2 times 10 exponent 7. So we're going to close parenthesis. 10, okay, I got everything there. So it looks like my decibels, well, they're huge. 197. So not like at 160 you can burst your eardrum. So let's double check that. Now let's look at the directions that we have here for rounding. It says round to the nearest whole number is needed. So if we took 197.9, it wouldn't stay 197. The 0.9 would raise it, the 7 to an 8. So what we would have here then is 198 decibels. So 198 decibels. 198 decibels. So now we have another question. This says, at close range, can the sound of this animal rupture the eardrum? Well, to rupture an eardrum, you need to be at 160, and we are way over 160. So I'd have to say yes. 198 is greater than 160. Therefore, the sound can rupture the human eardrum. So we have to be careful when we're comparing those values. Again, you compare them to 160 and go from there. As usual, if you have questions about the lecture, please bring them to class. You can stop by the Math Center or my office hours. Good luck on this assignment.